Hello, I'm Zach Stay.
And I'm Branden Greer.
Aaron Handy wasn't able to be with us today, but this is our process control project of a distillation column. So a common problem in crude oil processing is separating out aromatics and saturates from crude oil. And so to model this, we decided to design a distillation column that separates out benzene, an aromatic, and N-heptene, a saturate. We set a set point for how much benzene we want in the distillate. We decided that we would make a physical model using a physics-based model, and that we would receive disturbance variables of the inlet composition using data collected from a Mexican lab. For our physical model, we assume constant energy, volatility, feed flow, constant tray accumulation. We assume our column has 26 trays with our feed location at tray 13. These two equations calculate what the liquid composition is on each tray and the vapor composition on each tray. And it calculates it from the top and the bottom based on the flow rates and the volatility.
All right, to make this a control project, we wanted to measure XD, which is the composition out at the set point of 0.97 mole fraction. Then we control reflux ratio and fraction of feed flow through the bottom, F-bot, to be able to control the XD, and with the disturbance variable of the composition of the feed. As we found the relationships, reflux ratio tends to increase XD. As you'll see there, the response as it comes back up out of the doublet test. And F-bot likewise will increase the XD directly proportionally. Then when we modeled both the responses of reflux ratio and F-bot, we found that the FOPDT modeled the reflux ratio very well, and likewise the SOPDT was the best model for F-bot. That one was not as close of a decision for us to make, and so we went with those parameters, used IMC's tuning correlations to make PID controller parameters. And when we set up the PID controllers, we also looked at a parallel setup, but we found that this setup with the controllers in series is a great way to be able to use F-bot as something that has a much larger response on XD to make it changes to what it wants to do with the set point, and then the reflux ratio will make its changes to make a better XD process variable, which is then transmitted on the next iteration through our controllers in series.
So this graph shows our PID controllers with the IMC values. You can see that it's fairly accurate with our about a 1.5 overshoot at the beginning, and at the bottom it ends up with about a 1.52% variance with very little change in the reflux ratio or the F-bot. We decided to hand tune it to make it a little bit more accurate, a little more constant at our set point, and we ended up being very accurate. We only begin to slip off a little bit at the end when our reflux ratio caps off at the top, since the feed composition of benzene in the inlet is so low. For the physical volumes of the column, we calculated those to see how realistic our column was. We found that both our distillate and bottom compositions were very pure. In fact, the bottom composition is almost entirely N-heptene at the end. And our external flow rates are also very constant. However, the internal flow rates vary a great deal. For example, the enriching liquid flow on the bottom half of the column, the top half of the column, runs from about 2,000 moles per minute all the way up to 5,500 moles per minute, which would be very difficult to design a column that's able to handle that type of internal flow variance.
All right, in conclusion, we have those physical constraints with the internal flows, but we made a controller that was able to very closely keep the distillate composition to the set point, and in further work we want to make sure that we can keep those internal flows more constant. Thank you for your time and have a great day.